it is going to be extremely useful to consider magnetic field caused by a magnetic dipole. And a magnetic dipole consists of a current let's say I'm trying to make this, hey, I can't draw in 3 dimensions. This is a ring, such that right here, the current is coming out of the board, and right here, the current is coming into the board. Now, if I have this arrangement, then what's going to happen is I'm going to get a magnetic field. Well, magnetic field at the center. The magnetic field at the center is going to be outward. What I could do is I could take a tiny little chunk of the ring, and I could use the Biot-Savart law on that to find QV cross R, and let's see, QV downward, cross R outward, and that little chunk. The current is moving in that direction. R is radially outward. So, oops. So, to go from the Biot-Savart law to that tiny point, where the magnetic field is equal to a constant times I ds plus r hat over r squared. If this is the direction of I ds downward, and I am looking at this, because, sorry, R is going from this point inward, so R will be into the board there, which means that the cross product will be in the outward direction. If I set this up, what I'll find by looking across this is I'll get toward very close to one side, I'll get the magnetic field going out, and if I go to a distance to the other side, I'll get the magnetic field going in the opposite direction. So inside the loop, to one side of the wire, the magnetic field will be coming out of the board. To the other side of the wire, the magnetic field will be going into the board. So I get a magnetic field through this loop. Like so, and it'll fill all of the space. Now, the magnetic field caused on the axis at the center is given by mu naught I over 2 R, in this case, the difference between the two. So, if I have, let's take a step back and look for a moment at electric dipoles. And you may perhaps remember thinking back, darn it, we did not go and do huge chapters worth of work on the electric dipole. Why did we talk about the electric dipole if we weren't going to use it more? In large point, we talked about the electric dipole to be able to make a comparison with the magnetic dipole. Now, in the case of the electric dipole, I have two charges, positive and negative Q, separated by a distance S, and I defined an important characteristic of that dipole by drawing a vector P in the direction of S equal to the charge Q times the separation between the 2 points. Now, if we go back to those points, we have two cases where we have the location of the electric field on axis, which is 1 over 4 pi epsilon naught for space or air, times, 2 times that vector P, divided by Z cubed, where Z is the distance along that on-axis line from the center of the dipole to where we're looking now. That's the equation that describes the effect of the electric dipole on axis. Now, the on-axis magnetic field for a current loop is, okay, we had this as our simplified point on axis at the center. If we're not at the center, but we are on the axis, I can go through, we can show you how that comes about. I hope, and that's possible, there's ways you can go through the book, contact somebody else here. We'll go through where that comes from. But we have mu naught I, let me move this someplace with more writing room. The magnetic field on axis is mu naught I over 2 times R over the cube root of R squared over the cube of the distance of this. If I'm looking at some point out here at some distance R on the ring, and then some distance Z along the axis, then as I get farther from the center, this value 1 over R is actually R squared plus the quantity R squared plus Z squared to the 3/2 power. Now notice that if I go back to the center, where Z is equal to 0, this goes to R squared over R squared to the 3/2. R squared to the 3/2 is R cubed. R squared over R cubed is 1 over R. So we're back to this simplified level. But this is the magnetic field of that point on axis, where I'm going to call this as helpful is I'm going to say, look, make two simplifications, because the effect of the dipole is all about making simplifications in the space that we can. If we're ridiculously far away, oh, then we don't have to ignore, then we can, ignore this one little effect. If we're too close for it, we have to treat it as being distributed through space. But if z is way larger than r, then r squared plus z squared is basically z squared. And so at that point, the magnetic field on axis, on a scale where z is much larger than r is, that becomes mu naught I r squared over 2 z cubed. And I'm going to make this more helpful because, hey, r squared, that just represents something. But suppose I recognize, wait a minute, what's the area of this? The area of this is pi r squared. So I can write the magnetic field on axis for a magnetic dipole as being equal to mu naught I times A over 2 pi z cubed or say that I need myself some writing room, put it here, the magnetic field on axis for a magnetic dipole is not 1 over 4 pi epsilon naught, but mu naught over 2 pi. Or you know what? Let's put that back in the way that it had existed before. We're familiar with saying mu naught over 4 pi. So let's put mu naught over 4 pi times 2 times the current times the area over z cubed. And if I define mu, sorry, we have a different mu, we've run out of, honestly, different labels. If you look at the number of Latin letters plus the number of Greek letters, that's way less than the number of things we want to name. So if I define it like this, then the magnetic field for an on-axis magnetic dipole shows much the same form. It will show the form of mu naught over 4 pi as opposed to 1 over 4 pi epsilon naught times 2 times the vector mu over z cubed. So those will have the same form right there.